In the previous lecture, we discussed wind instruments. Now we're going to look at an example that deals with a certain wind instrument, and we're going to calculate the length of that wind instrument. So, suppose a certain wind instrument contains air 25 degrees Celsius. The pipe is designed in such a way to produce two successive harmonics at 250 Hz and 300 Hz. Knowing that information, how long is the pipe, assuming that the pipe is open at both ends? So we're going to break this problem down into 3 steps. In step 1, we're going to calculate the velocity of our standing wave inside our column of air. In step 2, we're going to calculate the harmonic number, and step 3, we're going to calculate the length of the pipe. So let's begin with step 1. So we want to calculate what the velocity of the standing wave is inside our pipe, inside our wind instrument, and we must use the following equation. So the velocity of air is approximately equal to 331 meters per second plus 0.6 T, where T is the temperature of the air given in Celsius. So we have 331 plus 0.6 times 25, and that gives us 346 meters per second. So this is the velocity of our standing wave inside the pipe that is open at both ends. Now let's move on to part 2. So in part 2, we want to calculate the harmonic number. So this frequency corresponds to a certain harmonic, and this frequency corresponds to a harmonic that is 1 plus this harmonic. So let's suppose this is n, then this must be n plus 1. So we want to find out what this n value is. So let's begin by realizing that these two frequencies correspond to two different standing waves, and the velocity of those two standing waves is exactly the same. In other words, the velocity of the standing wave that corresponds to the n harmonic is equal to the velocity that corresponds to the n plus 1 harmonic. And because the velocity is equal to the product of the wavelength and the frequency, we have the following two results. So the product of lambda n times fn is equal to the product of lambda n plus 1 and fn plus 1. So we can rearrange this equation to get the following result. The frequency n plus 1 divided by the frequency fn is equal to lambda n divided by lambda n plus 1. Now we know what this is. It's 300 Hertz. And we know what this is. It's 250 Hertz. So we see that lambda n divided by lambda n plus 1 is equal to 300 Hertz divided by 250 Hertz. And that is equal to 6 divided by 5. Now, notice in both cases, the length of the pipe remains the same. So that means the length of the pipe at the nth harmonic is equal to the length of the pipe at the n plus 1 harmonic. So recall that because we're dealing with an open wind instrument that is open in both ends, we use the following formula. The length of that pipe is equal to n times lambda n divided by 2. So, lambda n is equal to n multiplied by lambda n divided by 2, and ln plus 1 is equal to n plus 1 multiplied by lambda n plus 1 divided by 2. These two will cancel, and we rearrange our equation and find that the ratio lambda n divided by lambda n plus 1 is equal to the ratio of n plus 1 divided by n. Now we know lambda n divided by lambda n plus 1 is 6 over 5. So that means that lambda n divided by lambda n plus 1 is equal to 6 divided by 5, which is equal to n plus 1 divided by n. So that means our n is equal to 5. So now we use this fact and go to step 3. In step 3, we essentially want to calculate the length of the pipe. The pipe that is open in both ends. So once again, the length is equal to n times lambda n divided by 2. The n is 5. The lambda n, well, we don't know what the lambda n is, but we do know that lambda n is equal to the velocity of our standing wave, v air, divided by Fn. Now, v air is simply 346 meters per second. The Fn is given to be 250 hertz, and we multiply this division by 5, divide by 2, and we get approximately a length of 3.46. So this is the length of our pipe, of our wind instrument, that is open at both ends.